In this video, we're computing the net force on a golf ball. So we're told this golf ball is moving at 50 meters per second, inclined 30 degrees above the horizontal. And we have three forces acting on the ball. That's the weight pointing straight down, the drag force pointing opposite the direction of velocity, and finally a lift force perpendicular to the drag force and carrying an upward component. And the goal here is to get the net force, in other words, the vector sum of all these forces, and then express that in polar form, in other words, with a magnitude and an angle. So the basic strategy for vector addition is just to break all the vectors into horizontal and vertical components, find the net x component, the net y component, and then put those back together into polar form. Before we start breaking things into components, we need to label a couple angles that aren't labeled in the diagram. So to decompose the drag force into its components, I'm going to need this angle right here. And that's just the angle opposite this 30-degree incline for the velocity vector. So this is also 30 degrees. And then I know the angle between the drag force and the lift force is 90 degrees, which means this angle must be 60 degrees. And that's going to allow us to find the components of the lift force. And then gravity just points straight down. So it only has a y component. We don't have to worry about any additional angles there. So we start finding vector components here in the usual way. I'll just start with the drag vector, and that's what the x and y vector components look like. So we can label the horizontal one as an FDX. That is a vector, so we'll put a vector hat on top of it. And then we have our y component that we'll call FDY. So to get that x component, again, FDX, that's the adjacent side of the right triangle formed by projecting onto the horizontal axis here. So I just take the hypotenuse times the cosine of 30 degrees. So I have 0.350 newtons cosine 30 degrees. But we're going to use plus and minus signs to account for direction here. And because this points to the left, and we usually use rightward as the positive direction on the x-axis, this counts as negative. Next, we do FDY, and that points down, which is the negative direction for the y component. So I have a minus sign on that one as well. And its magnitude corresponds to the opposite side of this right triangle. So we're going to use a 0.350 sine of 30 for that magnitude. All right, next we're going to decompose the lift force into its x and y components. So there's the x and y components of F sub L, the lift force. And that x component, we're going to call that FL sub x. And the vertical component, we're going to call that FL sub y. So FL sub x also points to the left, so that's going to get a minus sign. And that's the adjacent side of this right triangle that we got by projecting our vector onto the horizontal axis. So for that, we're going to have hypotenuse times the cosine of 60, so 0.282 cosine of 60 degrees. And then FLY is going to be 0.282 sine of 60 degrees, and that one is positive because it points upward. Finally, we look at the force of gravity, and that points straight down, meaning the x component is going to be 0, and the y component is going to take a minus sign because we're pointing down here, so I have minus 0.441. And now we have all of our vector components in the x direction and the y direction. And so the strategy here is just to add up the x components and get a net x component. This can be done all at once in your calculator, and I'm just going to call this F. So I take negative 0.350 cosine 30 minus 0.282 cosine 60. And this gives me about negative 0.444 newtons. We do the same thing in the y direction. Just find the net y component by adding all these things up. And this gives me about negative 0.372 newtons. So those are the x and y components of the vector sum of all of these forces, but we still want to express our final answer in polar form. So at this point, we're going to draw a triangle to assist us. And for the horizontal leg of that, we're using our net x component, and for the vertical leg, the net y component. So there's our net x component and our net y component, vector added head to tail to get our net force on this golf ball. And that net force points from the tail of the first to the head of the second, as usual. Now the length of this horizontal side, I'm just going to write as a length now, is 0.444 newtons. And the length of that vertical side is 0.372 newtons. And what we're trying to do at this point is find the length of the hypotenuse. That's the magnitude of the net force that we call F, And we want to label a direction, in other words, an angle, and we usually do this relative to the horizontal. So I'm going to put that unknown angle right here and call that theta. So to find f, of course, we use the Pythagorean theorem. And I have the square root of 0.372 squared plus 0.444 squared. And this gives us about 0.579 newtons for the magnitude of the net force. Now for the angle, we can find that by using an inverse tangent. So this is the angle whose tangent is 0.372 divided by 0.444. Note that we're not concerned with measuring angles like relative to the positive x-axis and calling this an angle greater than 180 degrees. We typically just label an angle that's less than 90 degrees relative to the horizontal, and we just put a positive number on that angle, and the picture makes it clear exactly which way this force vector is pointing. So when I run the numbers on this and round to 3 significant digits, I get an angle of 40.0 degrees. So there's our net force vector on the golf ball written in polar form, and we're done. If you enjoyed this video or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.